Let's examine more problems related to common ion effects, and specifically we will now try to solve a problem in which both of the ions of the solid are already present in solution. We will also try to assess to what extent we need to keep track of all of them. So you have the general recipe, you build the ice table, you consider the amount that initially there was already in solution, but we will teach you some tricks so that one does not need to go to Wolfram Alpha or whatever other website you will use to solve that cubic or sometimes powers of 4 and 5 and 6 equations that may be hard to solve. Okay. In this case, it's asking for calculating the solubility of calcium hydroxide if in solution there is already a calcium nitrate. And this may be a common situation because our tap water contains a lot of nitrates and with calcium and sulfates, etc. And this means that what actually ends up precipitating is calcium hydroxide because our tap water already contains some calcium hydroxide. So first we will calculate the solubility of calcium hydroxide in neutral water with some calcium nitrate. Notice that this means that the concentration of calcium before any mole of the solid dissolves is already 0.1 molar. So how do we solve this? Calcium hydroxide will dissolve in water, okay, with some calcium and two hydroxides, both in water. So initially, this is solid. I have, how much calcium do I have? I already have 0.1 molar. Okay, before any solid dissolves, and I'm going to first assume that this is pH 7. So at pH 7 my concentration of hydroxide is already 10 to the negative 7. So now let's see when some solid dissolves, how much is that going to be? Well, it's going to be X here and 2X here. X being for each of the moles of the solid that dissolve, there'll be the same mole of calcium and twice as moles of hydroxide. That means at the end what you have is 0.1 plus X and 10 to the negative 7 plus 2X. This means my KSP, which is 6.5 times 10 to the negative 6, concentration of calcium, concentration of hydroxide square. Concentration of calcium is 0.1 plus X, concentration of hydroxide is this much square. Okay, again, this is a cubic equation. If you plug it into Wolfram Alpha, a cubic equation will give you 3 different roots. This is why it's cubic, but you will see that only one of them is positive, so choose the positive root, or the one that makes sense. Like if X were subtracting, you want to make sure that all your concentrations are positive, etc. Your X in this case is, if I'm not mistaken, 0.0395 molar. Okay. Now, in perspective, were we able to simplify our equations? Well, if this is 3.95 times 10 to the negative 3 molar, notice that in here this is pretty much just 0.1, and if this is 10 to the negative 3, you can consider this one kind of 0. So this really simplifies a lot your equation. Now you can just solve this with your calculator, okay, because then your KSP is equal to this. That means KSP divided by 0.1 multiplied by 2 root square. This would be your X. And notice that your X will give you a similar value as this one. Now, one cannot do that until it sees the extent of X. So careful with approximating until there are ways to know, but we will not ask you to be able to predict if you can simplify or not. However, notice that it's asking for the solubility at pH 1. What we can safely say here now is that, well, at pH 1, of course, the concentration of hydronium is 0.1 molar, which means by the autoionization of water, the concentration of hydroxide is 10 to the negative 13. So in here, instead of 10 to the negative 7, you would put 10 to the negative 13, which in this cubic equation, if x was already, no, I'm here, if x was already much bigger than 10 to the negative 7, this keeps being true, so I do not need to set up any equation, because what this was kind of almost 0 compared to the 2x. Now that we made 10 to the negative 13, it's even smaller. I can safely say that the pH 1, the x does not change, and the solubility is still the same. Okay, which in this case it's not surprising. Okay, again, one cannot do these simplifications unless realizes the extent of these values. So it's to be safe, just consider each and every one of the initial values and go ahead and solve it with Wolfram alpha, and that will definitely lead you to the right answer. Okay, now let's see if we can also understand qualitatively if the solubility will increase or decrease at, in this case, with the addition of H3O+. And to decide if any of these compounds will change the solubility when you add H3O+, one needs to apply the Le Chatelier principle. Let's use, for example, the one that we have used before, copper hydroxide, and I'm starting with this one, not with lead bromide, because you may connect this with our previous video. Notice that if I add H3O+, it means I'm decreasing the pH, and by decreasing the pH, it means that I'm decreasing the OH negative, and if I'm decreasing the OH negative, I'm decreasing the amount of products, and by Le Chatelier, the reaction will displace to the right. In other words, solubility will increase. Okay, so in this case, it's asking for what is the effect on solubility when you add hydronium. If you add hydronium to copper hydroxide, the solubility will increase. This is why we use vinegar. If you add vinegar to the stains on your sink, for example, that will typically dissolve the hydroxide solids that you have in forms of stains in your sink. So this is why you're actually displacing the equilibrium towards increasing the solubility. Okay. Now let's go back to this one, lead bromide. Does lead bromide is affected by solubility? Well, let's see. What we have here is just lead and bromide. Bromide, however, is a strong, so it's a conjugate base of a strong acid, is a spectator ion, therefore not affected by pH. Okay, does that make some sense? The bromide is a spectator ion, it's not affected by pH. If this were a weak base or a weak acid, it would definitely be affected by pH. Let's move to C. C is iron sulfite. Iron sulfite in solution dissolves with iron, and sulfite is a base. So if I am increasing the pH, what's happening? Now we need to write this equation. If I am decreasing the pH, I am adding protons. That makes sulfide disappear. Careful here. By adding hydronium, I make products disappear. That means the amount of products will disappear. How? Because I make them react with protons. Alright? If the number of products disappear, the Le Chatelier principle will displace the reaction to the right. That means the solubility will increase. Solubility will increase. Does that make some sense? In this case, we need to couple this. Notice that there is no hydroxide like in this case. In this case, we need to be able to realize that one of these react with acid, which is my weak base. Actually, this is a fairly strong base. All right, let's use another one. Calcium fluoride. Calcium fluoride dissolves into calcium and fluoride. Again, fluoride is a weak base that reacts with acid to form hydrogen fluoride. So by adding hydroniums, what I'm doing is I'm removing product. The product disappears. By removing product, it will displace the equilibrium to the right again, and solubility will increase again. Okay? Calcium oxalate. You may need to Google what oxalate is. Okay, it's if you are wondering what oxalate is, it's this coupled carboxylic acid. So it admits 2 protons. So calcium and oxalate. So oxalic acid is a diprotic acid. That means that oxalate admits 2 protons. So just by admitting one, it will remove the products from, so again, it will remove products from the equation, from the equilibrium. By Le Chatelier, it will be displaced to the right. The solubility again will increase. Okay. And finally, silver iodide. Silver iodide. Silver and iodide. You could say, well, iodide, I can make it react with protons. Notice that this is a strong acid, therefore the addition of hydronium ions in solution of silver iodide, that will not change the solubility. So no change for this one. Okay. So again, we'll keep practicing, but one can also use Le Chatelier principle to decide which of the solids be affected by the change of pHs.